Hi, I'm Nilay Sundarkar and I'll walk you through my CMU Capstone project, the HTAP Synchronization Research Assistant, a multi-agent retrieval um, grounded assistant for OLTP OLAP sync in HTAP systems. In plain terms, it's a multi-agent AI that helps people understand how modern databases keep their analytics in sync with their live transactions, and it does so with evidence and citations, not guesswork. Let's start with the problem. Modern databases like TIDB, Single Store, and LoyDB, Snowflake, and Oracle have to do two very different jobs at once. They handle fast live transactions, and at the same time they answer heavy analytical queries. The hard part is keeping the analytical side fresh without slowing the transactional slide down. The trouble is that the knowledge about how each system does this is scattered across academic papers, vendor documentation, and engineering blogs. And these sources often contradict each other. Vendors can't even agree on what real time means. If you just ask a normal chatbot, it can't cite its sources, it can't verify its claim, and it can't reconcile those contradictions. So it tends to make things up. This tool is built for researchers, engineers, and students who need answers they can actually trust. So here is the goal. The assistant takes a question, breaks it down, gathers evidence, weighs the option, and writes an answer backed by citation. To keep it focused, it concentrates on four key topics: how data propagates, how fresh the analytics are, how storage is compacted, and how the two workloads stay isolated. And it compares five well known systems. Importantly, it runs right out of the box, no setup and no API key required, which made it easy to test and demo. This is how it works under the hood. Think of it as an assembly line of specialized agents. Question comes in, it passes a safety check, and then a planner breaks it into smaller sub questions. There, those go to a researcher, which gathers evidence, and a critic, which judges the quality of that reasoning. Now, notice the loop between the researcher and the critic. That's the key idea. If the evidence isn't strong enough, the critic sends it back to search again with a broader set. Once the reasoning is solid, a synthesizer writes the final comparison, it passes one more safety check, and the user gets a cited answer. The whole thing is coordinated as a state machine, so every step is controlled and traceable. Let me quickly introduce the four agents by their jobs. The planner splits the big question into focused pieces. The researcher finds evidence and explores different possible explanations. The critic scores that reasoning and throws out the weak parts, and the synthesizer writes the final cited answer. I deliberately kept it to four. Adding more agents would have added complexity and coordination cost without actually making the answers more reliable. Here is what makes the answers trustworthy. For every sub question, the system pulls the most relevant and the most reliable evidence first. Then, instead of committing to the first explanation it thinks of, it explores several interpretations in parallel, a technique called the tree of thought, and keeps only the ones that are well supported and high confidence. And if the evidence is too thin, it automatically goes back and searches again. So the reasoning is always anchored to real evidence, not invented. Safe, safety is built in at every stage, on the way in, during retrieval, during reasoning, and on the way out. A few concrete examples. If the answer sounds overconfident, the system automatically softens that language. Every claim has to be backed by a cited source, and if the system just isn't confident enough, it flags the answer for human review instead of pretending it's sure. The goal is honesty, and the tool knows the limits of what it knows. I didn't build this all at once. It grew in stages, starting from the core concept, then adding memory and tools, then retrieval, then the reasoning layer, then the multi-agent coordination, and finally the safety systems. And at each stage, I deliberately simplified where I could to keep the whole thing fast, reliable, and able to run completely offline. To make sure it actually works, I tested it on a labeled set of questions covering all four topics. The evaluation tracks things like groundedness, whether claims are backed by sources, along with source accuracy, contradiction detection, um, and speed. And the whole evaluation is reproducible and runs without a paid model, so anyone can verify the results. Now, I want to be honest about the limitations because they matter. Today, it uses a built-in sample corpus. There is no live web or paper search yet. The search is lightweight and in memory, not a production-grade database. The reasoning leans on keyword and overlap heuristics rather than deep semantic understanding. It only handles text, no diagrams or tables. Its contradiction detection is fairly narrow. The evaluation set is small and it answers one question at a time rather than holding a multi-turn conversation. None of these break the architecture. They are deliberate simplifications to keep it offline and dependable, but they are the honest next things to fix. Which leads to where this goes next: real documentation, ingestion, and live search, smarter meaning-based reasoning and verification, diagram passing, a larger evaluation set, and a true multi-turn conversations. But the core takeaway is this: it's grounded, safety first research assistant, not a guessing machine. It's designed to give you answers you can actually check. With that, I end my presentation. Thank you.